Good day, everybody. I'm here to talk to you about Scott Krist's problem involving the pear orchard. I'm going to do this video assuming that you have read the problem already. That's a good habit in general. You should be reading the material before you go to class so you know what's going on. So if you haven't read the problem yet, go ahead and pause the video, do that, and then just come back and join us. So on reading the problem, you did see this chart here, or it's a graph rather, a graph that is very well labeled. It's got a title that tells us what data we're looking at. Well labeled axes here with the consistent scales, and any relevant points on our graph are clearly labeled with the ordered pairs that go along with them. And that's important because we're going to be using those ordered pairs to derive equations later on. So what is the basis of the problem? Well, the problem asks us to come up with a function that gives us the yield, that is the production in terms of pairs per tree, as a function of the tree density. And that is given in how many trees there are on a single acre. So as we can see here, with these three ordered pairs, if we have a tree density of 250 trees on a single acre, we're going to have 525 pairs on each tree. Likewise, if we have 280 on an acre, we get 480 pairs per tree, and 350 per acre, 375 pairs per tree. So as we can see just by visualizing the information, that as we plant more trees, the yield per tree goes down with it. It also does look like it is on a single line here, although we can't determine if these points are what we call collinear until we actually do the necessary calculations over here. So going back to the wording in the problem, it wants us to find a function of tree density, or a function that gives us tree density given the input of, a function of tree density that gives us the yield per tree. And it actually specifies the variable that they want you to use for density, which is x. So I've actually gone ahead and labeled that right here. And the function that gives us the yield in pairs per tree, it doesn't specify, the problem doesn't specify which letters it wants you to use. So I just went ahead and used t because we're talking about the yield per tree, t for tree, right? And I strongly encourage, when doing these problems, making sure that you have a little table here that relates all the variables that you're using to the actual items in the problem. So here we can see x is density, t of x is yield. And as the problem progresses, we're actually going to add more items to this list as we get more variables. So I've gone ahead and taken these ordered pairs here, and I moved them over here. And I just put them in this nice little table. These are all x values, and these are all y values. These are all values that appear on the vertical axis. So you have to go back and draw on your knowledge that you learned from intermediate algebra and all those classes, and come up with, or first try to figure out if these are collinear, which means they're all on the same line. And what that means is the slope between, if the slope of the line that connects this point to this point the same as the slope of the line that connects this point to this point? And if that is the case, then all 3 points lie on the same line. So I've done some quick calculations here that verify that for us. So y2 minus y1, so I'm taking the y value of one point minus the y value of another point, over x2 minus x1, I'm doing the same thing over here. So once I simplify all this, put it in my calculator, I get a negative 1.5. So this is the calculation I derived using these two. Right? These two these 2 points. And so this calculation is the same exact format except I've used these 2 points, right? These 2 ordered pairs. And again, I get the same result. So that definitely confirms for us that all 3 points are collinear. And that's very important because that means we can definitely use a line to model this, right? So in order to actually derive the entire equation, what we have to do is plug everything into our point-slope form. So we've derived what m is. M represents our slope. We plug that into this guy here. And we use any of the 3 points that we have here for x1 and y1. Right? y1, 375, x1, 350. So I'm using this ordered pair right here. And once I simplify that, I get a linear equation that tells us the production per tree given the tree density x. And the y here is just a placeholder, but in the end, this y is going to actually become t of x, our yield per tree in terms of x. Function notation is very much favored with these problems. One thing I would like to note is go ahead and make sure, I didn't do it right here, but make sure you pay attention to the units that you're dealing with. Because later on, when I do the second part of this problem, we'll see that unit cancellation and paying attention to our units is very important for ultimately solving the problem. So we've come up with this equation first, and in the next part we'll go ahead and show you how to come up with the quadratic equation. Alright, so we're going to go ahead and start part 2 of the pear orchard problem. So we've already come up with the linear equation that describes the yield per tree as a function of tree density. That's the number of trees on a single acre. Now, the next part of the question is how can we determine how many pairs are in an entire acre? So what we have here is we have, just an acre like this with a bunch of trees on it, and each of those trees has their own number of pairs. So how can we use this equation to determine exactly how many pairs there are on the entire thing, or on the entire acre?